Before we begin our discussion of electromagnetics, let's start with an introduction as to why E&M is so important. So the first question we want to ask is, where do we see electricity and magnetism? Pretty much everywhere. You have lights, electromagnetic phenomenon, televisions, mobile phones, radio waves. You also have computers and calculators, and cars, and even most living things like myself. Whereas inanimate objects run on electricity and light phenomena, such as rainbows, are due to electromagnetic behavior. The human body also needs electric signals for muscle contraction and neural signaling. So when was electricity discovered? There's actually this epic timeline of observations of electrical phenomena dating back to the Egyptians, but we'll only cover a few key milestones. So as early as 600 BC, the Greeks noticed that a piece of amber rubbed against cloth would attract straw. So they called amber an electron back then, so the Greek word was electron. Even before then, there were ancient Egyptian texts that said that there were electric fish in the Nile River. So these texts date back to the 28th century BC, and they called them the electric fish thunderers of the Nile. So it's pretty cool that electricity was observed way back when. In the 18th century, Benjamin Franklin made multiple breakthroughs in the field through his experiments. He was able to connect lightning and electricity through his kite experiments, which everyone has heard of, even growing up as kids. He discovered that opposite charges attract, while like charges repel. And he is credited for using the concept of positive and negative charge to explain electrical phenomenon via some sort of electrical fluid that penetrated all matter. So if you had more of this fluid, you would be positively charged, and if you had less of this fluid, you would be negatively charged. So nowadays, we actually know this as the electrons that move around, and that they can become negatively charged. So in 1784, Henry Cavendish, a great English experimentalist, defined the inductive capacity of dielectrics or insulators. In other words, the concept of a dielectric constant. So Cavendish had also discovered many laws a lot earlier before they were credited to other scientists. For example, he had the concept of electric potential, capacitance for a parallel plate capacitor, Ohm's law, and quite a few more. Next, we're going to move on to Charles de Coulomb, probably one you're very familiar with because you've probably heard of Coulomb's law, which is named after him. In fact, the units for electric charge, the Coulomb, or C, is named after him as well. So there is Coulomb's law, which is an inverse relationship, and the unit of charge is Coulomb. Now let's start our discussion of electric charge by looking at the atom. A modern day picture of the atom is presented here, where the central nucleus is made up of positively charged protons and neutral neutrons. And then it's going to be surrounded by a cloud of negatively charged electrons. So the nucleus has both protons and neutrons, and both protons and electrons have the same magnitude of charge, being 1.6 times 10 to the negative 19 coulombs, or C. So after that, we'll explain coulombs as a unit in a bit, but while we're on the topic of protons, neutrons, and electrons, we know that protons and neutrons are in the nucleus, and because of that, they have the same mass of 1.7 times 10 to the negative 27 kilograms. And the electron mass is different, so keep in mind they're not going to be the same. The electron mass is 9.1 times 10 to the negative 31 kilograms. So when the Greeks first discovered electricity by rubbing amber with fur, they didn't understand what was happening. Nowadays we do. For any neutral atom, like the one that we see here, the number of electrons and protons are the same, and the total charge is 0. Although protons are tightly bound in the nucleus, the electrons can easily move around in the outer bands and can be removed or added. Since the electron holds a negative charge, removing one is going to give the atom a positive charge, and adding an electron is going to give the atom a negative charge. So now, let's try to explain what the Greeks observed. When rubbing two objects together, small amounts of charges, in other words, electrons, are transferred from one object to another, and this is called the triboelectric effect. So when we rub two objects together, small amounts of charges are going to be transferred from one object to the other one. And the question now is, how do we know which direction the charges are going to move? So different materials are going to have different tendencies to give or take electrons. So some of them want them, while others don't, and give them away very easily. So a triboelectric series gives us the tendency of materials to acquire a positive charge, or basically which materials are going to like donating electrons. So the triboelectric series can be shown here with this table, and the farther up you go up that table, the more likely that material is going to acquire a positive charge or donate an electron away. So let's go through some examples. Question number 1, if I rub amber with fur, what is going to happen? And that's what the Greeks did. If we rub amber with fur, although fur isn't really on the chart here, it's actually quite high up the triboelectric series, which means that it's going to prefer to acquire a positive charge or donate a negative charge away. So it will want to lose electrons, and when we rub it against amber, the electrons are going to move from the fur to the amber, making the fur positively charged and the amber negatively charged. So what about rubbing a glass rod with silk? We know that glass is really high up the triboelectric series, almost at the very top, so it's going to want to donate electrons to become positively charged. This means that it's going to transfer its electrons to the silk material, making the silk negatively charged due to the excess electrons, and the glass positively charged